The Clean Power Hour is brought to you by the Clean Power Consulting Group. I'm Tim Montague, your host. Check out all of our content at cleanpower.group/podcast. Please give us a rating and a review on Apple or Spotify. That's how other people will find this content. Please also subscribe to our YouTube channel. When you go to cleanpower.group, just click on the YouTube icon and that will take you to our channel. Today on the Clean Power Hour, zinc for battery storage. Storage is so vital for the energy transition, and my guest today is the founder and CEO of a company called Enzinc. They're developing next-generation zinc rechargeable batteries for electrification of transportation, for stationary storage, and many other applications. Welcome to the show, Michael Burz.
Well, thanks very much. I really appreciate it, Tim.
Excited to learn more about your technology and bring this to our listeners who are very familiar with us talking about storage here on the Clean Power Hour, mostly about lithium-ion storage. Your technology is a little different, so we're going to break that down. And why don't you start by highlighting your background and why you got interested in zinc technology for energy storage?
Certainly. My background is aerospace engineering, so have done many projects, high-tech projects ranging from the advanced cruise missile to Nissan's car to race at the 24 Hours of Le Mans. I was interested in taking my expertise in both program management, business, and high technology to see if we couldn't apply that to green technology, helping advance, a green technology revolution. We started looking at electric vehicles and what type of energy systems would be good for them. Luckily, we met some people at the California Nanosystems Institute, run by University of California, Los Angeles. And they introduced us to the work they were doing on zinc, three-dimensional zinc. And it was actually money that was funded by the Office of Naval Research. And they were looking for an alternative to lead-acid batteries, as well as lithium-ion. And that then hooked us up with Dr. Deborah Rollinson at the US Naval Research Laboratory. And they were looking at how to make zinc a high-performance battery as an alternative to lead-acid and lithium-ion, because they had some very bad experience with lithium-ion batteries. So we've been working with them for many years in taking zinc from just the three-dimensional structure that could be used for a disposable battery and turned it into a rechargeable battery. And so that's what we're working on, is essentially a high-performance alternative to both lead-acid and lithium-ion. It's a battery that has the energy of lithium-ion, but kind of the ease of manufacture and low cost is lead-acid, but is safer than both of them to use for people as well as for the planet.
Yeah, and lead-acid technology is very widespread. It's in our internal combustion engine vehicles. It's in our EVs as a auxiliary battery. And the challenges with lead-acid are, one, it's very heavy. The Navy is using lead-acid in submarines. And, submarines need to be very quiet, which is why they want to operate on electric motors if they can. And lead is toxic. Now, and then of course there's lithium, which is lighter and has very good energy density, but it has this tendency to catch fire, or what people would call thermal runaway in the industry. And so lithium is a double edge. It's being used en masse now in EVs, so it does work. And, obviously Tesla and Nissan and Hyundai and Volkswagen and many other companies,
General Motors, yeah.
Right? GM and Ford are going after this now. So explain how zinc technology is attacking, so to speak, both the lead acid and the lithium industries, and then I want to really do a deep dive into your strategy, which is quite unique, I think. You gave up seemingly just going full bore after the EV market directly to make a EV battery. Is that right?
Somewhat. So let's talk about first kind of what's the advantages of this particular technology and why it's applicable to both the mobile as well as stationary energy storage as an alternative. So the first thing that this zinc anode does that makes zinc applicable is that it gets rid of dendrites for zinc, right? So dendrites, as your listeners may know, are needle-like formations that form on charge and discharge. And these can then grow rapidly in zinc, short out the battery, and kill it, which is kind of the problem that Thomas Edison ran into when he patented in 1901. What our sponge structure does, and we can talk about it in more detail later if you'd like, but it eliminates dendrite growth, which means that now zinc can be used for many, many cycles, not just several hundred cycles, but thousands. And we've demonstrated that with an ARPA-E, a U.S. Department of Energy ARPA-E award. The second thing it does is it has high surface area. It's a sponge structure, of course. So that means you get high utilization of zinc, which means you get high energy and high power. And the third is that it's cathode agnostic, which means it can be coupled with nickel or silver or manganese or carbon for a zinc air battery. So now you have a full application suite. So in terms of the energy for mobility, as compared to lead acid batteries, it has about 3 times the energy and 3 times the cycle life of a lead battery. So that means you can have things like start-stop vehicles. You can have lighter batteries in your internal combustion engines. In fact, Tim, you and I had talked about, we won an award at GAMIC, which stands for the Global Automotive Mobility and Innovation Challenge. And that's sponsored by the Society of Automotive Engineers. One of the judges was from Ford and asked, so why do I care about this particular battery? And I said, I used to drive a Ford Explorer, and the battery in that, the lead battery, is about 30 kilos. We can deliver you that same power, same energy for about 10 kilos. You save 20 kilos right off the bat with doing nothing but changing it. And you and I know how much the automotive energy will pay to save, a couple of kilos on a car. For the electric vehicle range, we have a specific energy which is equivalent to lithium iron phosphate at the cell level and nickel metal cobalt at the systems level. So why do I say that? Nickel metal cobalt batteries need a cooling system. They need a sophisticated battery management system, and they need armor to protect them. So by the time you take the cell level specific energy, which is around 220 to 240 watt hours per kilogram, add those systems, the effective specific drops to about half. And therefore, you end up with about 120 on average, watt hours per kilogram. We don't need any of those. We don't need thermal management. We don't need a sophisticated battery management system, and we don't need armor. So it turns out from a systems perspective, if you take a look at vehicles which are urban electric vehicles, those which are less than 300 kilometers, e-bikes, e-scooters, delivery vans, passenger vehicles, like taxis within an urban environment, our battery then is extremely compatible Whereas vehicles that are high performance that go greater than that, much longer ranges, 400, 500, 600 kilometers, lithium ion is awesome. So what we'd like to think of this is by 2030, most of the people in the world are going to live in an urban environment. And so we provide that kind of alternative to lithium ion for electric vehicles that will essentially help free up some of that supply chain pressure that lithium is under, which means it can help bring down some of the costs for them, which means electric vehicles can be used by everybody for different applications.
Now, what are the components of the end product that you're planning to make versus off the shelf today, lead acid or lithium ion? I know that you're attacking some of those critical elements, but can you get rid of all the lead in the lead acid battery, or is it then a hybrid?
So what we're looking at is, for this application initially, is a nickel zinc battery. The next battery we'll be looking at is a manganese zinc battery. And that will literally then replace any lead that's in. So the battery would be a one-for-one replacement for a lead battery.
Okay. That has its own hazards, I believe, though, right? Because nickel is not necessarily easy to get your hands on either, is it?
So the amount of nickel around at the moment, of course, is under pressure. But there are additional resources in countries that are not necessarily unfriendly to the United States that have enough sufficient capacity to supply that. And we certainly don't need, by the way, the amount of cobalt that lithium batteries need to keep the nickel stable, because we're not looking at that that high energy density that they are. So we don't need any of the amount of cobalt that the lithium batteries need. So it makes the nickel that we use a lot easier to get.
So let's talk about, the next 5 years. What is the status of the technology today, and what products will first come available to manufacturers and ultimately consumers?
Right. So we have kind of this two-pronged approach, as you alluded to. So there's mobility batteries and stationary energy storage. So let's talk about mobility first. We're going to start off with a fairly small battery. It's for an e-bike. We're building a prototype e-bike for one of the largest e-bike manufacturers in California, and they're going to be testing that battery. So it's a 48-volt battery, about 900 kilowatt hours. What's fascinating about that one is we can build it in a small form factor, test it, modify it, and then deploy it rather rapidly. But as you know, and many of your listeners know, the automotive world is also looking for 48-volt systems for the internal combustion engine. So we can then scale that battery relatively easily for those kind of 48-volt internal combustion engine systems.
How
The
many
same
kilowatt
thing
hours
will
did you say? Because that sounded like a big number.
about 900 watt hours.
Okay.
Yeah, just under a kilowatt hour. Sorry,
Yeah.
thank you.
No worries.
Then what we're going to do is we'll be able to scale that same battery for use in e-rickshaws as well as those urban electric vehicles. So in the one hand, as I said, the mobility, there's the small battery that we're building now that can be scaled for both urban electric vehicles and internal combustions. We can then take that battery once again, because we can scale these anodes rather rapidly in terms of size, to go for stationary energy storage. And simply by rewiring the internals of the battery between parallel and series cells, we can then go for larger size batteries for either microgrids, data centers, industrial applications, and for localized microgrids. So, by the way, you asked about our time. We're developing the e-bike battery, mobility battery now. We should have that one finished in terms of prototype by the end of this year. We'll be testing that and our manufacturing next year, and it should be then available in 2024. The stationary energy storage will follow that by about 6 months to a year for the full deployment.
Okay, so e-bikes, you mentioned rickshaws. I mean, are you in discussions with manufacturers in Asia? Because it seems like that would be an earlier adopting market perhaps than even the US. Of course, people are using small EVs and e-bikes in the US, but they're using them en masse in places like India and China. And I guess related to that is why isn't everyone kind of dogpiling into this arena, or maybe they are?
So, uh, excellent question. So I'll give you kind of an extended answer. So the first part is, are we talking to people? And the short answer is yes, we are. We're under NDA with many of them, so I can't tell you who they are. We formed what's called an industry advisory group. There's about 10 companies that are involved in it. 4 of them are multi-billion-dollar companies that are interested in the technology. And we are talking with people in India, Bangladesh, and other countries in the area. Why aren't people leaping into this? Number one, batteries are fundamental. They're foundational to everything that everybody's using. And so almost every manufacturer that we've talked to is suddenly part of the state of Missouri, right? They're all show me. So we have to go through extensive development and testing with them before they're going to adopt this. But I think, as you know, and you've alluded to, we have a somewhat unique approach to how we're going to do this.
Hey, everybody. Thanks for listening to the Clean Power Hour or viewing it on YouTube. We do have a great YouTube channel. If you're not subscribed, please go to cleanpower.group and hit that YouTube icon and subscribe to our channel. Of course, you can find all of our content on your favorite audio platform as well. So please give us a rating and review. Back to the show. Yeah. And yeah, I mean, reducing the volume or the weight of the battery by a factor of 3 is very good. I guess I'm struggling a little bit to understand the potential impact on the energy transition. And when I say energy transition, I'm referring to electrification of transportation, uh, greening the grid, meaning solar, wind, and battery storage for grid power, and then electrifying everything else, heavy industry, and building space conditioning. What kind of broad strokes can you paint for us in terms of your role in that bigger picture? I get the feeling that it's a both and, right? You're not saying that you're going to replace lithium ion, you're going to augment lithium ion and lead acid for that matter, although maybe replacing lead acid initially will be more of a impact. Is that right?
That's correct. So, for example, the e-rickshaws that we talked about, they typically use 4 to 5 large 12-volt batteries to do that. And we can replace that with one battery, which means that you either save cost, you can carry more load or more passengers, and of course, for the e-rickshaw operator, they can operate for longer times on the battery, both in terms of discharge times as well as the number of cycles, which makes it more economical for them. The same thing goes with, the urban electric vehicle size or the e-bikes. What we're also keenly interested in is deploying the technology in a highly dense urban environment in which, you want to couple solar with storage for those growing developing countries that are trying to put in their own grid infrastructure. And that way we can make sure that they have cost-effective but very safe batteries that you don't have to worry about thermal runaway. And then there was one other advantage, particularly for those kind of deployments, is that the temperature envelope for the battery is much more like lead acid, and it doesn't require kind of a thermal management system, which means that it reduces the cost as well as increases the reliability for those kind of deployments. So for instance, we can go to storage at about minus 38 degrees C, storage up to 65 to 70 C, operational at about minus 30 C to about 60 to 65 C, which means for very hot or very cold climates, you can make a very simple, cost-effective deployment.
Yeah, that is a real weakness of lithium technology for all kinds of applications. You have to have this conditioning system, right, to keep the battery either warm or cold or cool it off in extreme temperatures, and which we increasingly have because of climate change. So I really like the safety factor here, right? There's zero risk of fire, if I understand correctly, or thermal runaway with the zinc technology, which is why the military is so interested in it. So what, you know, what is holding this back? What are the challenges that you have to overcome in order to, bring this to market and, speed the energy transition?
Just like every piece of new technology, the people that are going to use it really need to be shown, that it deliver.
Mm-hmm.
So for batteries, when you're promising a particular performance parameters, you have to actually demonstrate those. We can only go so far with computer simulations, basically saying, yes, based on the data in the lab, that this will last 1,000 cycles, 2,000 cycles, and so on. When you get to the point of getting ready to deployment, you actually have to demonstrate that, which means months and months and months of testing in both a real world environment, hot, cold, and so on. So there's going to be a lot of extensive testing. But what we want to do to help move that forward is do two things. This industry advisory group, we've invited them to be part of our development program early. And so they get some of the necessary inputs into our test program as well as the results so that we can help speed that testing acceptance along. The second thing we have to do is to be able to deploy this technology in a rapid fashion. So what we've done is decided we're not going to be a battery company. We're going to be an advanced engineering battery development company to take advantage of this zinc technology. We will test and qualify these batteries for these manufacturers because many of them do not have their own R&D facilities around new chemistries. We'll develop that, but the one thing that we've done is develop the battery so that it can be built in an existing lead-acid factory or a nickel metal hydride plant by simply replacing the anode and the cathode with the nickel zinc or the manganese zinc, and then you can use all the rest of the equipment the same. So we can essentially turn existing capital equipment from building legacy batteries to high-tech batteries and turn them into gigafactories with very, very small capital investment.
And so, if I hear you correctly, you are not planning to become, for example, a CATL or a Samsung that is mass producing battery cells and battery packs. You are going to partner with existing manufacturers and help them integrate your technology, your IP, into their technology. Is that right?
Yeah, in a fashion.
Okay.
We've decided to take a page from Intel.
Mm-hmm.
So we want to become the Intel of batteries.
Mm-hmm.
So the same way that Intel has the chip technology, and then they work with computer companies to design the computer around that chip, and then they build the computer, and Intel sells them millions of chips. And that's what we want, is kind of an Enzinc inside on the side of the battery. We'll help develop that. They'll build the battery and take advantage of their existing high-tech manufacturing, their large-scale manufacturing, their established sales and distribution channels, and their brand, and we will sell them millions of these things, zinc anodes.
Okay. And so you will be in the business of manufacturing,
Absolutely.
just not a finished product per se that goes to a consumer or goes to an
Correct.
EV maker. It's going to be the battery companies, the battery manufacturers themselves that will buy your product. Okay.
That's right. So we'll
Well,
help
what
it. We'll
else?
help them advance to a high-tech battery,
Hmm.
but they will actually build the battery. They'll have their name on it on the side, and we'll just supply them with these things.
Yeah. So let's recap a little bit. You've got the for one thing, it's zinc, which is already a readily mined and available material. Um, I guess we didn't talk about that supply chain directly yet, so maybe we should think about that. But you've got a technology that has no thermal runaway risk, so uh, you will get potentially broader adoption from markets that have held back on lithium, for example. You have an existing infrastructure that you're just basically tapping into. You're not building gigafactories. The battery manufacturers are busily building those factories, and so in a way, your go to market is less costly. The number of cycles that you can get out of a battery is very high. Is it as high or higher than lithium ion?
Depends upon the chemistry.
Mm-hmm.
We've already done 1,000. Our next target is 1,500, and we believe our ultimate goal will be 2,000 cycles. Lithium iron phosphate, depending upon the type of application you're looking at it, is claiming like 4,000 cycles. But in terms of the cost, by the time you'd look at kind of the dollars per kilowatt hour per cycle, we're very equivalent to lithium iron phosphate.
Okay.
And by the way, the supply chain you asked, zinc is the fourth most mined metal on the planet. They typically do between 12 to 14 million tons per year.
Mm-hmm.
It's mined just about everywhere. We can then process it and use it and quickly deliver without any kind of supply chain issues.
And what about the end of life and recyclability? How recyclable is the technology?
Oh, excellent. We're actually working with one of the world's largest recycling firms to have them be part of our design process at the beginning. The battery can be recycled just like a lead acid battery, whether it's the zinc manganese or the zinc nickel version. But yes, that's one of the major features of it. And we're working with them to make sure that we have a complete circular approach to it so that we can mine the material, but then once we're finished with it, we can reuse the material, both the nickel and the zinc and the plastic and so on, to create new batteries, or at least repurpose the material for other things. Zinc is used for galvanizing, for fertilizer, for medical purposes. And once we're finished with it, it could also be deployed to those applications as well.
Okay. Well, what else should we talk about? I don't know what I don't know, and obviously you've been working on this for a while. Um, what do you see in your crystal ball, so to speak, and what kind of a signal? I mean, you mentioned this consortium that you've established, which sounds very positive, and and you've already won numerous awards, in niche markets. So what else should our listeners know?
So one last thing. As I said, I'm an aerospace engineer, and we actually kind of got into looking at zinc because I think that the next generation battery that we'll be working on, the advanced version, is the Zinc Air battery. And the one really cool thing about this is that it's a sponge structure, and it doesn't have to be just flat. We've actually made some with compound curvature to it, which means that I can make a battery that fits into the wing or the fuselage of a drone. And then with the high specific energy that we have and really relatively simple materials like zinc and carbon, I'm looking forward to our battery advancing electric aircraft as well. That will actually be a safe, high-performance alternative for electric airplanes, and not just delivering Amazon packages, but actually delivering people.
Well, that's very cool. I've been watching the electric aircraft market somewhat at a distance, but it's noteworthy that, Norway, for example, has set a timeline for all the regional aircraft to be electrified, I think by 2030 or 2035. So that market is definitely coming. Certainly for short distances, like up to 200 miles. Um, but that would mean that your technology should be very applicable to longer range electric vehicles as well, no?
So Zinc Air,
Mm-hmm.
yes. Okay. However, the one thing that makes it applicable for aircraft is because, they travel a long distance, then they can wait. But with cars, you don't have a set route, right? You could drive for 30 miles, you could drive for 300 miles. And the one thing about a Zinc Air battery is it's only effective when it's breathing. So in other words, if you drive for only 30 miles, you have to then provide a system that shuts off the battery from the air so that it's not discharging. So it's one of those systems things that I think for cars, it could be interesting, probably more interesting for trucks because they have a very, very long distance that they travel at each time they do it. But airplanes do the same thing. So for certain applications, the Zinc Air battery, I think, will be really, really competitive and really interesting, particularly when we project that the installed specific energy will be greater than 250, probably closer to 300 watt hours per kilogram at an installed location, and for really relatively small cost because the components are zinc and carbon.
And what is the difference between Zinc Air and the zinc that you're currently, or the zinc technology that you're currently pursuing?
Right. So the battery that we're looking at the moment, is this nickel zinc battery, and then followed by the zinc manganese battery. The Zinc Air battery requires that system be able to oxidize and reduce from zinc to zinc oxide and then back to zinc again. And we want to be able to do that efficiently with a carbon air cathode. And to do all that efficiently in one job still requires some work to do. So yeah, we're still going to be looking at that as in development in the long term.
And is that Zinc Air technology analogous to the iron air batteries?
Yeah.
Okay.
But we discharge a lot quicker than the iron air batteries.
Mm-hmm.
And there are lithium air batteries But as you know, lithium and moisture and salt do not work well.
Yeah.
So you have to do a lot of air conditioning to make sure that you don't get an adverse reaction with the lithium, whereas we don't have to worry about that.
Yeah. Understood. And how far away are we from Zinc Air?
Probably about 5 to 7 years
Okay.
before we can see that kind of technology.
Okay. Well, is there anything we didn't discuss that you'd like to touch on?
Only that we've recently been awarded a bridge award from the California Energy Commission. And so we're ramping up rapidly. And if I can use your podcast to basically say we're looking for some excellent engineers to work with us in both battery design, testing, and manufacturing to set up our automated plant for making these anodes. Because right now we're doing these by hand. And what we have to do, of course, is turn them into, well, I like to think of it as there's a great bakery in San Francisco known as Tartine that makes some of the best products in terms of croissants and tarts and so on. So right now, we're kind of the Tartine of making zinc anodes, and we need to become like Nabisco and turn out graham crackers by the millions.
Indeed you do. Well, Michael, I really appreciate you coming on the show. I want to make just a couple of quick announcements, and then we'll let our listeners know how they can reach you and apply for a job at Enzinc. Check out all of our content at cleanpower.group/podcast. Please give a rating and review on Apple or Spotify. That is the best thing you can do besides listening to the podcast yourself. But giving a rating and review will help others find the show. And then also click on that YouTube icon and subscribe on YouTube to our channel. I really love hearing from my listeners. So if you have an idea for a guest or a technology that you'd like to see us bringing onto the show, please reach out to me. That's how most of the guests come to me, is just through active listeners and technologists at companies. If you're a technologist, would love to hear from you. With that, I will ask you, Michael, how can our listeners reach you and your recruiter?
Really, really simple. Just go to the website, www.enzinc.com. There's the careers section there, as well as our info at enzinc.com, where you can contact us, questions, and we'd be happy to help you out.
Excellent. Well, I'm Tim Montague. Let's grow solar and storage. Have a great day, everybody.